me if a large fraction of the room has no idea what I'm talking about. So what is this course about? So the first thing is, using randomness in algorithm design and analysis. So you've probably seen in your algorithms course that sometimes problems are difficult, and sometimes having access to random coins makes algorithm design easier. Take, for example, quicksort. If you assume that true randomness exists, and you're actually allowed to pick random sets from your array, then suddenly sorting becomes substantially easier. I'm not in this course at all going to go into the philosophical discussion. Does true randomness exist? Does it not? What does our world look like? I will just pragmatically assume that, well, we have access to random coins. And interestingly, even if the world is fully deterministic, it's turned out that thinking in terms of randomized algorithms is really useful in order to design deterministic algorithms. As we'll see sometime during this course, that some of the algorithms that we design using randomness on the first few days, we'll see how to turn them into deterministic algorithms towards the end of the week. And it's often not obvious how to design deterministic algorithms for those problems of that type from scratch without thinking of randomized algorithms first. So it ends up being a very natural and good stepping stone. So the randomized algorithm you probably already know is quicksort, probably hashing, and that's all in the context of polynomial time algorithms. So in this course, we're going to be talking about randomized algorithms in the context of coping with NP completeness. So we're going to be looking at problems which provably don't have polynomial time algorithms, unless p equals np and the world explodes. But okay, we don't have polynomial time algorithms, so now what can we do about it? And the naive view of your problem is NP complete as well, then you can't do anything. You should solve a different problem. Now we don't want to be quite that pessimistic. We'll look at what does it really mean for a problem to be NP complete. Well, you know that if your problem is NP complete, then there doesn't exist any single algorithm that solves all instances of the problem optimally in polynomial time, right? So most of the time in this course, we'll be dealing with optimization problems where I give you some input and I'll ask you to find the best possible blah. Yes, I give you a map, find the shortest path from A to B, or I give you a set of data points. What is the minimum number of data points you need to remove so that the remaining of your data is pairwise consistent? Like get rid of all inconsistencies, etc., etc. So it will often be easy to find one feasible solution. Just remove all the data. Then it's definitely pairwise consistent, but you want to delete as little as possible. Or it's easy to find some path, but maybe it's harder to find the shortest path. So if your problem is NP complete, then you have no algorithm that is going to solve all instances optimally in polynomial time. And the proof that will lead to something strange uses all three. So if you have an algorithm that, for example, doesn't solve all instances, but solves some instances optimally in polynomial time, there is no contradiction. And therefore, we can start asking, well, can there be such algorithms, even though my problem is NP complete in general? And I hope that some of you have seen algorithms like this before. So for example, the independent set problem. So here input is a graph G. and that your goal is to find a largest possible set of vertices so that no pair of these vertices have an edge between each other. All right, so let me just get a gauge of the audience. Can I get a show of hands if you've seen this problem before, independent sets? All right, good. I'm going, okay, so as you see, I'm starting gently and the course is going to pick up, right? So this is, hopefully in the beginning, you'll feel like you know everything. And by the end of the course, hopefully you'll be feeling that now you know everything. Neither will be true. Okay, so the independent set problem is NP-complete in general, but it's really easy to solve if your input graph is a path, right? Just pick the leaf, kill off his neighbor, pick the leaf, kill off his neighbor, keep going, yes? If it's a maximum weight independent set is a little bit more tricky, you can try to think about how to do that, but it's still possibly perfectly doable in polynomial time. So even though your problem can be NP-complete in general, you might be able to solve it in polynomial time if you can make some assumption about the input. Now, what about approximation algorithms? Well, if you can't always output optimal solutions, you might be able to output some feasible solution with some guarantee on how good it is, right? And what precisely some guarantee on how good it is, what that guarantee is, we'll see in a little bit. Most of the time, we're going to be comparing the solution output by the algorithm with the best possible solution for that instance that could possibly be achieved. And so if for every instance, your algorithm outputs something that is not more than a factor 10 worse than the optimum solution to that same instance, then what you have is a 10 approximation algorithm. Now, we'll also be looking a little bit at exact exponential time algorithms. So most problems do have silly brute force algorithms. If those are subset problems, they typically run in time 2 to the n, right? So even say independent sets, this problem that I mentioned earlier, has an easy 2 to the n algorithm. Just loop over all possible subsets of the vertices, check is this is independent set or not. For the ones that that is, keep the largest one. Now the question is, can we do better, right? Can we do, instead of 2 to the n, can we do 2 to the n over 2? And the next question is, well, if you do 2 to the n over 2, why should we care? Because as theoretical computer scientists, we've been trained not to care about constants. And now suddenly we care about this constant divided by 2 in the exponent. Well, we care about constants when they are in the exponent, right? Like you care about n squared versus n because we just square rooted the running time. And if you try to do the math, then if you go from 2 to the n to 2 to the n over 2, you also just square rooted the running time, right? So dividing the exponent of an exponential time algorithm by 2 is qualitatively the same improvement as going from n squared to n. And so, you know, one should care. Famously, there's a nice quote that for every polynomial time algorithm, there's an exponential time algorithm I'd rather run. Because of course, if you have an algorithm with running time 1.0000001 for a sufficient number of zeros, then that is going to beat n cubed for the values of n you actually care about. So as Sakit pointed out, my area of research is very often in parameterized algorithms, which sort of straddles between the exact exponential time algorithms field and the restricted input field. We're saying, well, let's not restrict our inputs at all to some specific subclass, but let's rather have some measure of how difficult the instance is, where when the measure is big, then it's a completely general instance. And your algorithm should run in exponential time because, you know, if it ran in polynomial time, you would be proving that p is equal to np. But when the measure is small, then your instance is very restricted. And so you should have algorithms that run fast. And of course, everything in between. So you want to have this sort of smooth interpolation between, on one extreme, the restricted input case, and on the other extreme, the exponential time case. Okay, so that was sort of a brief overview of the fields that we're going to be looking at this week. In all of them, we're going to be applying, randomness in order to design and analyze some fun algorithms. And today is going to be an approximation algorithms day, mostly. Not quite, but most of the algorithms we'll see are approximation algorithms. So here's the problem we're going to look at first, max cut. So what is max? So what is max cut? I give you as input a graph G, and I ask, find me a set of vertices that maximizes the number of edges with one endpoint in one side of, like, in the set, and one endpoint out of the set. So delta S is this set of edges that leaves vertex set. Okay. So this problem is known to be NP complete. Again, it has a 2 to the n easy algorithm. But now we're going to ask, well, can we do something reasonable in polynomial time? Yeah. So of course, we'd like to prove something, right? We'd like to say, we'd like to give an algorithm that always outputs a set of vertices. That's easy, but now we want to say something about the quality of that set. Yeah. And precisely what that is, we're going to see in a little bit. But the algorithm we're going to do is the stupidest algorithm you could come up with. Namely, pick a set of vertices uniformly at random, output that. Yeah. So I will often use some abbreviations, and if I forget to tell you what those abbreviations are, you should ask. Yes. So UAR just means uniformly at random, which means that for every vertex, you include it in the set S with probability 1/2, and you make that choice independently for every vertex. So here's your algorithm for max cut. Just pick a random set, output that set as your solution. So can we prove anything interesting about it? Well, then we need to analyze this random process, because now picking a set of vertices uniformly at random is a random process. It has an output, namely S. So S is a random variable, right? It's something that before you throw your dice, you don't know what its value is. Yeah. And in your stats class, you probably have only seen random variables whose value is a number, right? Now you should revise that, as in your object-oriented programming class. A variable can take any object as any type of object as a value. So a random variable can also take any type of object as a value. Yes. So you could have random variables whose value is a vertex or a vertex set, which is precisely what we did right now. Okay. Now, what properties does a vertex set have? Well, it has a size, and it also has this property of how many edges are leaving, this vertex set. Now, that is a random variable of type, number, integer. And for random variables whose type is an integer, there's a well-defined, most of the time, expectation, right? So I hope that you now remember back to the definition of expected value of a random variable from your stats class. And let's ask ourselves, okay, do you remember what is the definition of the expectation of this random variable? Well, here it is, right? It's the sum over all possible values that the random variable could take of that value times the probability that it takes that value. Yeah. And now here's a question. We picked a random set, yeah, and then I ask you, what is the expected value of that set? We threw out the definition. And in order to compute the definition, well, we only need to sum up to n, which means that we only need to compute these probabilities for every value of I from 1 through n. Yeah. Now, can someone compute this for me for an arbitrary graph? Okay, let me turn the question around a little bit. I'm claiming that computing these probabilities is NP hard. It's at least as hard as the max cut problem. So I'll give you like 20 seconds to think about this. Why is it that computing these probabilities, if you have an algorithm that could always do it, you would also be able to solve the max cut problem?
Probability is greater than 1 by 2, then we know that the size is for the max cut.
Yes, so in particular, if for some value of I, the probability is non-zero, yeah, then there exists at least one set S whose cut size is I, right? So if I knew the probabilities for all values of I from 0 up through n, right, then I would take the largest I for which the probability is non-zero, and that's the value of my max cut. So, okay, I have this stupid random process. I picked a random set and I want to analyze its expected value. For this, I need to compute its probabilities, but I can't compute the probabilities because that's as hard as solving max cut. All right, let's leapfrog over this problem and compute the expectation anyway, because we can. So the trick we're going to do is to not use the definition of expectation, but rather use something called the method of indicator random variables, which is something that we're going to be doing in this course over and over and over again, which is also why I'm doing this really slow. So for every edge, indicator random variables are random variables that each one are either 1 or 0, and they're indicating something. Did something happen? Did something not happen? So in this case, for every edge in the graph, let me define a random variable xe, which is 1 if the edge is in the cut, and 0 if it's not in the cut. So in the cut means one endpoint on one side, the other endpoint on the other side. Now, there's a silly observation, which is, of course, that the size of the cut is the sum over all the edges of 1 if the edge is in the cut and 0 if it's not, right? If I go over all the edges and I count it, if it's in the cut, then I get exactly the number of edges that are in the cut. And in particular, we now know that the sum of xe's is a random variable. So the expectation of the size of the cut is the expectation of this sum of random variables. And now you have to think back to your intro to stats class. And there, one of the first things you learn is the expectation of a sum is the sum of expectations, right? Linearity of expectations, does it ring a bell? E of a plus b is equal to e of a plus e of b. And I remember when I was sitting in my stats class and the professor said this, I was like, okay, whatever. It has an easy proof and you never come back and really use it in the stats class. It's like one of those random facts that you learn. It has an easy proof. Sometimes it shows up on the exam and you write it out and like, I never cared. The thing that you didn't realize when you were learning this in stats class is that you were learning dark magic. It's a miraculous trick that just helps you solve so many things. So here is the first example. The expected size of the sum is nothing but the sum of the expectations. So the sum of the expected values of xe's, even though these random variables xe's could be arbitrarily complicatedly dependent on each other. Right? The expectation of a sum is the sum of the expectations, even when your random variables are dependent. So now all we need to do is to compute for each edge the expectation of xe for that edge. Well, okay, well, what is that? Now we can apply the definition, right? The expectation of xe is 0 times the probability that xe is 0 plus 1 times the probability that xe is 1. Well, the 0 term disappears, so this is nothing but the probability that xe is 1, which I claim is 1/2. Why? So why is the probability that xe is 1 equal to 1/2?
There are two vertices and each vertex has been different sets.
Yeah. Right. So in order to figure out whether the edge is in the cut or not, all we need to know is for each of the two endpoints, whether they are in S or not. So you have 4 possibilities: U in S, U not in S, V in S, V not in S. And out of those 4 possibilities, 2 of them end up leading to the edge being in the cut. And each of the 4 possibilities have the same probability, namely 1/4, 1/2 times 1/2. Okay. So in particular, for every edge, the expectation of xe is 1/2, right? So what does that mean? It means that the sum of the expectations is the sum over all edges of 1/2. There's m edges, you get 1/2. First time I saw this, mind blown, right? Because what just happened, right? We have this expected value, which if we want to compute the probability that the random variable takes individual one of those values, it's provably NP hard to do it. But the aggregate, their average, is so easy to compute. Yeah, and in particular, it also turns out to be something that's fairly large. It's like m/2. Half the edges are cut on average. Right? So even though this problem is NP complete, when you do something maximally stupid, right, you pick just a random set, you cut at least half the edges, which means whatever the best cut for the graph was, well, it's never more than all the edges, right? So you're never a factor more than a factor 2 worse than the optimum, which is the definition of a 2 approximation algorithm. So here, you know, in expectation, we're always outputting m/2 edges, right? Okay, but here's a question. What does expectation even mean? Right? Like when I say in expectation, we're outputting m/2 edges, we have to think back again to your stats 101 course and like, what is expectation? Well, expectation is the following thing. If for any graph G, right? If I keep doing the stupid thing, right? Like I keep sampling a set S1, and I see how many edges does it cut. I keep sampling another set S2. How many edges does it have? And I keep doing this forever. And then I take the average. Then that's going to converge to the expectation, right? But that doesn't mean that every time I sample, I'm going to get something that is close to m/2 edges, or I'm going to get at least m/2 edges, right? What I care about for this problem is I want to see at least one cut with as many edges as possible. In this case, let's say at least m/2. And there is no guarantee that this sampling process doesn't have this pathological behavior that like every time you sample, it just gives you some really small number, like m/10, right? Like you sample, you get m/10. You sample m/10. You sample, you get m/10. But then sometimes, like very rarely, it gives you some huge number, so that the average still ends up being m/2. Yeah. So now we should ask ourselves, okay, if in expectation you're getting m/2, how many times do I need to repeat the experiment before I'm fairly certain that I have seen m/2 at least once? Yeah. So before I do this, let me, I've put that in here. Let me put out one thing, and that is at least that, the probability of getting at least expectation, right? The probability of getting at least m over 2 edges is non-zero. So for any random variable that is number valued, the probability of getting at least expectation is greater than 0, and the probability of getting at most expectation is greater than 0. And this is just the law of averages, right? Like if you have a bunch of people, you take their average height, there will be at least one person of at most average height, and there will be at least one person of at least average height. Because if everyone was bigger than average, then the average would be bigger. So this is actually the first instance of us having proved something that has nothing to do with randomness using randomness. I claim that this proves that for every graph, there exists a set of vertices that cuts at least m over 2 edges. Why is that? Well, because the probability of cutting at least m over 2 edges is non-zero. For every cut, the probability that you get that cut is 1 over 2 to the n. So, okay, there has to be a cut that cuts at least m over 2 edges. Yeah. So this is an example of what's known as the probabilistic method, where you take some statement, right? For every graph, there exists a set that cuts at least half the edges. Take a statement that has nothing to do with probability, and then you apply some random process and say that, well, it will give you this kind of object that you look for with non-zero probability. Right? Yeah.
I just want to sort of ask about one slightly sneaky thing there. So the fact you've written greater than equal to and less than equal to.
Yes.
That's important in one of them, right?
It's important in both because everyone could be average, right? You could have a situation where suppose everyone has exactly the same height. Then there is no instance of anyone deviating from it. Yeah. Thanks. More questions? Okay. Let's see. This is what we just said. And now I'm back to this question that I asked earlier, right? We now know that there exists a set that cuts at least m over 2 edges. Can we find it? And how many times do I need to repeat the experiment before I stumble upon such a set? Okay. In order to do that, we need to ask ourselves, well, what can the probability distribution of a random variable look like with a given expectation? So for example, you can have a random variable that is 0, almost certainly, right, with probability 1 minus 1 over 1 million, and it's 1 with probability 1 over 1 million, and then its expectation is 1, and that's of course a typo. I meant, let me fix it. Here we go. Useful for these live talks. There we go. So if you have a random variable that is 0, almost certainly, with probability 1 minus 1 over 1 million, and 1 with 1 million with probability 1 over 1 million, then its expectation is still 1. Right? But if I try to sample this random variable, and I sample it for not that many times, the only thing I'm going to experience is 0, 0, 0, 0, right? So now we need to ask ourselves, well, can we say anything meaningful at all about how many times we need to resample before I see a cutoff size m over 2 at least? And for that, we're going to use this wonderful theorem called the Markov inequality, which states the following. For every random variable that is always non-negative, so suppose So for example, it's like the height of people or the number of edges that you cut, right? Because you're never going to cut minus one edge. It holds that the probability that you are at least 2 times your expectation is at most 1/2. And this holds for every value of 2 that is bigger than 1. So in particular, the probability of being at least 3 times expectation is at most 1/3. The probability of being 10 times expectation is at most 1/10. And I'm not going to give you the proof for this, but the intuition is the following. No more than half of the population can be at least twice as tall as the average. Because if more than half of the population were at least twice as tall as the average, even if everyone else had height 0, the average would be more than the average. Okay, so, you know, I gave you a tool, I gave you a question, let's apply the tool to the question. So let's apply the Markov inequality to the question. Well, what's the probability that the size of the cut is at least expectation, right? And what you get is utter nonsense, right? Because one, the inequality is in the wrong direction. Why? We're trying to so what do I mean by the inequality being in the wrong direction? It is that even if I had a probability up here that was, let's say, 0.5, then I'm saying that the probability that the cut is at least expectation is at most 0.5. That's not what I need. I need to know what's the probability that my cut is at least expectation, and I want it to be at least something. And this is another thing that is going on in randomized algorithms all the time. Inequalities are your friends. Right? Like you'll be very tempted lots of times to like compute probabilities exactly, and that is going to lead you into a nightmare of computation that you can't get out of. So you really want to be, you know, as lazy as you can and use inequalities everywhere, but you have to make sure that they're in the correct direction. Yeah. And for that, you have to think, okay, what is it that I'm trying to prove? Well, what I'm trying to prove is that the probability that it cut is at least something. And that probability, I want it to be at least something, right? Now the second thing is, of course, that what?
I mean, the first inequality is in the right direction. That is not the wrong direction.
Well, I mean, the two inequalities are the combination of the two inequalities is the wrong direction. Okay, I mean, it's like. Yeah, I mean, like you either want to say that the probability, like right now, the thing inside the probability is the thing that you want to happen. If you flip the inequality, then it will be the thing that you don't want to happen, and then it's okay to upper bound its probability, right? Okay, so you know the first attempt at using our tool to answer our question didn't work, and then. What do? Well, you reformulate the question so that you can answer it using the tool, right? That's somehow if you have a hammer and that's the only thing you have, then you just have to find a ways to use the hammer, right? So let's define a random variable to which Markov inequality actually will give us something useful. Namely, let's define x to be the number of edges that are not cut, right? So x is m minus the cut edges, yeah? Then, by linearity of expectation, okay, we see it a second time today, the expectation of x is the expectation of m minus the number of cut edges, which is the expectation of m, which is m. It's not a random variable at all, minus the expectation of the number of cut edges, which is m/2, so that's m/2. Right? So notice that the expected number both of cut edges and of uncut edges is m/2. Now you can do a sanity check in your mind. This makes perfect sense because if you complemented the graph, yeah, that would make sense. Okay, no. Now I said some utter bullshit. Erase that. Okay. If you complement the graph, you're getting n choose 2 minus m/2. Okay, so I didn't say any of this. Okay. Okay, we defined x as this number of edges that are not cut, and we computed its expectation, it's m over 2. Now let's apply Markov inequality to the number of edges that are not cut. Right? So notice we are interested in the probability of the following good event. What is the probability that when I pick a random set, the number of cut edges is at least m over 2? Right? Well, I can write that as 1 minus the probability of the bad event, namely that the number of cut edges is strictly less than m over 2. Yeah, which is then equivalent to saying that the number of cut edges is at most m over 2 minus 1/2. Because, you know, the number of cut edges is an integer, m over 2 is some multiple of 1/2. So if you compare a multiple of 1/2 with an integer and one is strictly less than the other, then they're at least 1/2 apart. Okay, so now we want to turn this around because we want to apply Markov inequality, and Markov inequality compares a random variable and it's interested in what's the probability that the random variable is bigger than something, right? So now we flip which random variable we look at. So if the number of cut edges is less than or equal to m over 2 minus 1/2, that's equivalent with the number of uncut edges to be at least m over 2 plus 1/2. We're still not quite on the form of Markov inequality, right? Because Markov inequality says that if I want to now upper bound this probability, right? And Markov inequality says if you're comparing a random variable with its expectation times something, right? Like times 2, then that probability is at most 1/2, right? But now I'm in a little bit of trouble because, well, okay, I have a random variable greater than its expectation plus something. Yeah, I want it to be times something. Right? Now it's back to your undergrad calculus class, right? Like when you want times something to appear, you multiply and divide by it. Yeah, so you multiply by 1. So here it is. My iPad starts replying. It's not. Okay, it's exciting.
Actually, I don't understand transition from the situation to the next.
Let me like wrangle the technology and then I'll answer your question. All right, that's exciting. Is it so? Is the Zoom still working? All right. So we're going to take a quick 2-minute break while I restart this machine.
Okay, so 1 minute is not good.
What? I mean, the whole thing is frozen. All right. Hard reset. Come on. The poor iPad, what isn't used to doing screen sharing. I don't know. I have actually done this lots of times. What?
Do you want to use the backup iPad and go?
I have a computer for that I can use as a backup. but it should work out. Yeah, this is going to take like 3 minutes. So whoever is on Zoom, you can go get coffee or something. Yeah, we'll resume in like 3 minutes or so. Neil, can you come up here for a minute? Can you come up for a minute? There's, for some reason, it's not connecting to the guest network. Everything that's, let's see, so. And it won't connect me to EduRoam here either, so I just neither one of these.
This I have visited and made a password for you. I haven't changed it.
Oh, okay, now I understand what was going on. Okay, it's my iPad decides to log on to the VPN. Okay, that's why it's not working. No, it's not gonna, well, let's see, maybe it will work. But, okay, yeah. No, go back. No, go back, it's not gonna work right now.
Hmm?
Yeah, it sees it logged off. It's because, no, I just need to, okay, no, it allows it, let's see. Because the guest one won't let me connect to the VPN, and the VPN is connecting automatically. And there's like, okay, there we go. No, on the.
Can you check if one node is studying?
No, it was. I mean, it just. Oh, wrong one. Sorry. Mail and this first, and then yeah, it just the whole thing froze up. It wasn't. Okay, so am I hosting it? Oh.
Okay, yeah.
All right. I think we're back online in a minute now. Okay, it's doing the thing. Okay, just give me a minute. There. All right.
Recording in progress.
Great. Can you make me co-host again? Yeah, I'm gonna. All right, and we're back. Except for, there's some way of turning on sound. All right. Can you mute me maybe? That's interesting. Oh, okay, because what's going on is that my sound is on and I cannot turn it off, unfortunately. Yeah, it is already all the way down. Yes, 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 yes. There we go. I think I did it now. Okay, so. Excellent. All right. So sorry about that break, technology. I hope you remember where we were because I've totally forgotten everything. Okay, so we were in this thing that that an expectation, when you pick a random cut, the size of the cut is m/2, and we are trying to lower bound the probability that when you pick a random cut, you actually get something of size at least m/2. And we did it, and we are doing it by considering another random variable, x, the number of uncut edges whose expectation is also m/2. And we have now reformulated the probability of the good events that we care about, namely that the size of the cut is at least m/2 in terms of this other variable, which was 1 minus the probability that the number of uncut edges is at least the expectation of the number of uncut edges plus 1/2. And now there was a question, and now I can take your question. Why does this line follow from that line? That was the question. So why does this line follow from that line? Well, because there's a 3.5 line in between those two, where we're doing the following. We're saying, well, if the number of cut edges is at most m/2 minus 1/2, that means that the number of uncut edges is at least m/2 plus 1/2. Yes? And the expected number of uncut edges is precisely m/2. So from the line between here and here, we just changed m/2 to ex. Yeah, is that okay? Okay, and now, we need to turn this on a form where we can apply Markov. And I said multiply and divide by something. Okay, so the probability that x is at least ex plus 1/2 is, let's multiply and divide by ex, right? Because now we're interested in what's the probability that x is at least ex times something. So how do we get that? Well, we multiplied it and divided by ex. So now we're interested in the probability that x is at least ex times something. And Markov says that that is at most 1/something, right? The probability that you're at least ex times 2 is at most 1/2. Yeah. So we blindly apply Markov, and what do we get? Well, it's that it's at most 1/something. What is that 1/something? It's ex divided by ex plus 1/2, which is m/2 divided by m/2 plus 1/2. Yeah. And now 2 is common, so it goes away. So it's m/m plus 1. Right? And m/m plus 1 is what? It is nothing but 1 minus 1/m plus 1, right? Because m is famously known as m plus 1 minus 1. And m plus 1/m plus 1 is 1 minus 1/m plus 1. Cool. So, you know, we succeed with probability at least, well, yeah.
I think we need a 2-minute break because the Zoom camera stopped working and the online people are not able to see.
Technology. All right. All right. All right. So can you guys hear me again? All right. So I'm not going to do this again in the interest of time, but what we did some calculation magic and ended up at the setting that the probability that the probability that the bad event happens, namely that x is at least expectation plus 1/2, is at most 1 minus 1 over m. So it's a probability that is bounded, like the bad event happens not with probability 1, right? It happens with probability slightly less than 1. So if the bad event that you don't want to happen happens with probability, less than 1, that means that the good event happens with probability a little bit more than 0, right? So now we can come back here and say, well, the probability of the good event is at least 1 minus 1 over m plus 1, which is 1 over m plus 1, right? So when I pick a random cut, the probability of that cut having size at least m over 2 is at least 1 over m plus 1. Yeah. Well, that's a pretty dismal probability of success, right? I mean, it's something pretty low. However, it's not that bad. It's like 1 over a polynomial in your input size. And as we'll see that, like, even though 1 over polynomial in your input size is bad, it's not that bad. Why? Because if you try once and you don't succeed, what do? You try again. There's some feedback happening again. Yes, I do. Let's see. Okay. So if at first you don't succeed, then try again, right? So if you don't succeed, so if your success probability is 1 over m plus 1, or if suppose your success probability is 1 over 10, right? Then how many times do you need to try again before seeing at least one success will be at least 1/2? I was like, how many times do you need to repeat until you have constant probability of seeing at least one success? Yeah. Well, we can calculate this, right? So what can we do? Let's repeat t times and pick the best solution, right? Like pick a random cut t times for some value of t, pick the best one. If any one of them is more than m over 2, we're very happy. Right? So now we're going to ask, well, what's the probability that the best of t solutions has size at least m over 2? Well, it's 1 minus the probability of all solutions that we've got having size strictly less than m over 2. And we know that for each individual one of those, the probability of it being size strictly less than m over 2 is 1 minus 1 over m plus 1. Right? Let me. Right, I'm talking about. So for every individual solution, the probability that that solution is bad is 1 minus 1 over m plus 1, right? What's the probability that the 2 first solutions are both bad? It's 1 minus 1 over m plus 1 squared. What's the probability that the 3 first solutions are all bad? It's 1 minus 1 over m plus 1 cubed. All t, well, it's to the power t. And the probability of at least one good is 1 minus the probability of them all being bad. Yeah, so this is where we are. Okay, and now we're left with this 1 minus 1 over m plus 1 to the t. And here comes the inequality, okay? When working with probabilities, there is one inequality that rules them all that you have to remember. It's not 1, it's 4. But in particular, this is the inequality. It's 1 plus x is at most e to the x. Because probabilities often involve small numbers, x, think of x as some probability, right? This translation, like e to the, and when x is tiny, 1 plus x is often very close to e to the x. And it's often really, really useful to transform something on the form 1 plus x to e to the x. Why? Because we're very often multiplying things, right? Like when you have some independent events, their probability is very often some product of independent probabilities. Yeah. When you apply the inequality, you turn this into a product of e to the power something. And a product of e to the power something turns the product into e to the sum in the exponent. And sums are much easier than products to analyze. Therefore, this inequality is super useful. Right? So if there's one thing you got to remember is that 1 plus x is at most e to the x. By extension, 1 minus x is at most e to the minus x. Yeah. There's 2 more that we're going to see sometime later in this class, but I'm not going to talk about them so much yet, but they're in the notes. Okay. So where were we? We were here. It's 1 minus 1 over n plus 1 to the t. We apply the inequality that this is at least 1 minus e to the minus 1 over n plus 1 to the t, which now translates to e to the minus t over n plus 1. Okay. A little bit of, is the inequality going in the right direction? 1 minus x is less than or equal to e to the minus x, right? That's the one we applied. So in particular, we replaced something smaller by something bigger, but it has a minus in front of it. So we're subtracting more. So the inequality is in the right direction. Okay, sanity check completed. Okay, so now the exponents multiply and you get 1 minus e to the power t over n plus 1. Now what should we choose t? Because we wanted our failure, this is our success probability, right? We have a chain of equalities and then finally an inequality. So we're saying that our success probability is at least something. And we want that at least something to be constant. Right? So if I pick t to be m plus 1, this ends up being 1 minus e to the minus 1. So 1 minus 1 over e. Right? So if I pick t to be equal to m plus 1, then my success probability is 1 minus 1 over e, which is at least 1/2. So at least half the time I'm succeeding. So what does that mean? So like if I pick a random cut and I do this m plus 1 times, then with probability at least 1/2, at least one of these cuts will cut at least half the edges. Yeah. And of course, if I repeated this, if I pick m plus 1 to be 100 m plus 1, then my success probability will be 1 minus 1 over e to the 100, which is 0.999999 for something like 10 nines or even 12 or so. So like once you get success probability 1/2, then boosting it by repeating it a few more times will bring your success probability really, really close to 1. Yeah. So in particular, this analysis goes through for any success probability, right? Like 1 over m plus 1 isn't special. I could have 1 over 1 million, repeating it about 1 million times gives me success probability 1 minus 1 over e, right? Like what success probability 1 over n squared, repeating it n squared times gives me success probability 1 minus 1 over e. So in particular, we should always think about success probability to be the inverse of running time, right? Or like 1 over success probability, you can just think of that as a factor in your running time, because that's how many times you need to repeat everything in order to succeed at least once. Yeah. So, okay, and this is our little moral that if you have success probability 1 over r, we need to do about r trials to get success probability roughly 1/2. Okay, now notice the time per trial is order m, right? Pick a random thing, count how many edges got cut. We need to loop through every edge. The number of trials is order m, so the running time of this algorithm is m squared. So we have an order m squared time algorithm that always outputs, or with probability 0.999999, outputs a cut of size m over 2 at least. As I observed earlier, for any graph, m over 2 is at least half of the optimum, and therefore this is a 2 approximation algorithm, right? So the definition of a factor 10 approximation algorithm is that on every instance, the algorithm runs in polynomial time, outputs a solution that is no more than a factor 10 worse than the optimum. For a maximization problem, that means its value is at least opt divided by 10. For a minimization problem, means that its value, the value of the solution it outputs is no more than 10 times the optimum value. Okay. Breather, ask some questions, and then in the next, 25 minutes, I'll do, instead of max cut, I'm gonna go min cut.
Could you please repeat for the time per trial? How it's order m?
Why is it order m for time per trial? Well, what do you do in every trial, right? You pick a random set, right? So that's order n, right? You just flip n coins, 1 for every vertex. And then you need to go through every edge and check whether it was cut or not, right? So if your graph is given, let's say, as an adjacency list, you loop over all the vertices, you loop over all the edges incident to that vertex, and you just check whether the coins for that edge had different value, and then you count it or not. Yeah, so it's... More questions? Okay, so we've done max cut. Now let's do the polar opposite, namely min cut. Right? Suppose I give you a graph G, and now I tell you, give me the set of a set of vertices so that the number of edges going out of that set is as small as possible. And then you're going to tell me this is trivial, just output the empty set. There's no edges that leave the empty set. Then I'm going to tell you, no, don't pick the empty set. And you're going to tell me it's still trivial, pick the set of all vertices. Because there's no edges that leave the set of all vertices. And then I'm going to come back and tell you, well, you can't do that either. Okay, and now the problem becomes interesting. Right? So find me the minimum cut that actually has at least one vertex in and at least one vertex out, and now you're minimizing the number of edges that cross the cut. Okay. Turns out this problem is much easier than the max cut problem. You can solve it in polynomial time. Possibly in your algorithms class, you learned max flow min cut. But that's max flow min cut for a given ST. So you want to find a minimum cut that cuts some vertex S from some other vertex T. Then you do some clever things and use some heavy machinery and out comes an algorithm. And of course, now I could go over all possible choices of S and T and solve the min cut problem in polynomial time. Right? Okay, if you didn't follow whatever I just said, it doesn't matter because what I'm going to do is give you a completely different algorithm. So if what you're trying to do is to just find a cut that rather than for a fixed S and a fixed T, trying to cut that, but instead you're just trying to find the minimum non-trivial cut in the graph, you can do something that is much easier than trying to run max flow. So in order to explain you this algorithm, I need to tell you this notion of a contraction. So what's a contraction? Suppose I have some edge in my graph, UV, then I take the two endpoints of that edge and I pinch them together, right? So that's what the picture is. So in particular, if my vertex had an edge going to U or it had an edge going to V, right? Then now it's going to have an edge to this new UV vertex that I got after a contraction. Yeah. And it's convenient for us to allow double edges in the graph because of reasons that you'll see in a little bit. So if I had an edge going to U and one edge going to V, now I have two edges going to UV, as you see in the picture. So that's the contraction operation that we're going to use. So what I'm going to do, I'm going to analyze this algorithm. Start with a graph that's supposed to find the minimum cut. And it does the following, again, really silly looking thing. It picks a random edge, and then it contracts it. And then it picks another edge, and it contracts it. And then it keeps going until the graph has two vertices left. Yeah. Now, when the graph has two vertices left, then what happened? Let me draw the picture, right? You started out with some graph, and now you have two vertices left, let's say X and Y, and because we kept multi-edges, there were lots of edges between them. Yeah. But every vertex in the graph that used to be there, it went somewhere. Where did it go? You know, either to X or to Y. Yeah. So you had some vertices, let's say big X, that got contracted into little x. You had the rest of the vertices, big Y, they got contracted into little y, and that's your cut. Okay, so I'm going to say, let S be the set of all vertices contracted into X, output that as a cut. Well, okay, this is an algorithm. It clearly runs in polynomial time, right? We didn't do anything smart, right? We just pick an edge contracted, pick an edge contracted. In every round, the number of vertices goes down by 1. So after n rounds, n minus 3 rounds, there are 2 vertices left. So it always, the algorithm always terminates in polynomial time. It always outputs a cut. It does always output a set of vertices. So really what we're interested in is, what is the probability that we actually output a min cut, right? So suppose there is some hidden min cut in the graph, such that the number of edges leaving it is C. We're interested in knowing, well, what is the probability that the number of edges leaving the cut that we output is actually C? Yeah. And we're going to prove something that is even stronger than that. We're going to say the following. Let C be some unknown optimum cut, right? Like if there is a cut that cuts at most C edges, just pick one, call it big C. Yeah, I'm going to refer to both the cut and its value as C. The capitalized is the cut, the non-capitalized is its value. If you call everything by the same letter, then you maximize confusion, which is what we want. What?
It cannot be less because C was the value.
Exactly. So less than or equal to is what we're shooting for, right? So less than or equal to just means equal to. Yep. Okay, so now the question is, what is the probability that S, the cut that the algorithm outputs, is actually equal to this unknown hidden optimum cut? I mean, not in terms of the number of edges, in terms of that is the exact vertex that you output. Yes, because there can be lots of optimal cuts. You just pick one and you ask, what is the probability that you output this one? And here is the funny thing. Suppose I have some fixed unknown cut C. I claim that my algorithm will output C if and only if no edge of delta C is ever contracted. Yeah. Why is that? Well, I mean, here is delta C. So here is C. Delta C is leaving it. Yes. If all I do is I contract edges on left and right, then eventually this will be pinched together. This will be pinched together in one vertex, and this will be pinched together into one vertex, and then I'm going to be outputting precisely C. Yeah. And of course, the moment I contract an edge of C, then I can never output C because there's 2 vertices of C that will both be on my in my cut now. Yeah. So this is an if and only if. So to analyze the probability that I output C, what I have to do is analyze the probability that no edge ever gets contracted? Well, okay. What's the probability of this happening? So first, why did I put K? Okay. So now we have to switch our brain. C was the size of the cut, but then in my notes now K is the size of the cut, so K is the new C. Yeah. So K is now the size of the cut. If I have M edges, yeah, and K of them are in the cut, and I'm trying to pick one edge, and I ask, what's the probability that this first edge is not in the cut? Well, I have M minus K options that are not in the cut, and I have M options total. So that ends up being M minus K over M. Yeah, that's the probability that the first edge I contract is not in the cut. Okay, now let M2 be the number of edges left after I contracted that edge. Yeah, now I didn't contract an edge of the cut, so all of those K edges are still left. So now in the second round, the probability that I don't pick an edge of the cut is M2 minus K over M2. In the third round, it's M3 minus K over M3 and so on. Yeah, so it's a product of this long product, and we want to figure out what it is. Now, to bound this product, here is the crucial observation, that the number of edges in the graph is at least the number of vertices times the cut size, the optimum cut size, over 2. And this holds for every graph. Why is that? Well, a possible cut, right? Like when I was asking you to not give me trivial cuts, the trivial cuts were like everything and nothing. What's the closest thing to a trivial cut? Let's just cut one vertex away from everything else. That's likely to have few edges, right? It might not, but that is fairly likely to be close to an optimum solution. So if I have a vertex of degree K, yeah, then that vertex is my, like cutting that vertex away from it is an optimum cut. So if opt cut is K, min degree is K. Yeah, and now handshake lemma, right? If the minimum degree in the graph is K, then the sum of the degrees is at least nk over 2. Yeah, so that's exactly what we did. Yeah, m is at least n times minimum degree over 2. But then that holds for every graph, even every multigraph when you allow multiple edges. So in particular, this holds at every stage in our process. Right? At every stage in the process, however many edges we have is at least however many vertices we have times k over 2. Yeah. So now we can rewrite this product of, you know, m1 minus k divided by m1 by n1 times k over 2 minus k divided by n1 times k over 2. Yeah. So notice I replaced m1 by something smaller. Yeah. Now it takes a little bit of thinking that you're allowed to do that, and the inequality is going to still go in the right direction. But you can think about it like this, right? If you have 1000 minus 5 divided by 1000, yeah, and then you compare it with 900 minus 5 divided by 900. You're dividing by less, but you also have less in the numerator. So which effect is stronger? Turns out that the dividing by less effect is stronger. Okay. You can sit down and then work out it, and I'm not going to do it. Okay. So now, okay, so I can replace m1 by n1 times k over 2. I can replace m2 by n2 times k over 2. I can replace n3 and so on. And now what happens is that things cancel, right? Like I can multiply here by 2, yeah, so that I get times 2 here, and the divide by 2 goes away, right? And then the n1 times k, the k up top is a common factor. Yeah, so I can factor it out. Let me undo it in case I'm working in the wrong document. Here we go. Okay, so now I'm getting this. So I'm getting n minus 1 and n1 minus 2 times k divided by n1k times n2 minus 2 times k divided by n2k and so on, right? So now the k's cancel, right? Because I have a k factor both in the numerator and the denominator, and I'm getting this wonderful product n1 minus 2 over n1 times n2 minus 2 over n2 and so on. Okay, so now let's see if you guys are still awake. Ni, so n1 is the number of vertices I have before I contracted anything. Yes. So n2 is the number of vertices I have after I contracted one edge. N3 is the number of vertices I have after I contracted two edges. So what is Ni? Yes, and that value, and if you started with n vertices, then how many are you left with? So n minus I plus 1, right? Yeah, because every time you contract, you lose 1. Yes. Okay. So in particular, what does this mean? Right? You're getting n minus 2 over n times n over 3, n minus 3 over n minus 1 times n over 4 minus n minus 2, and so on and so forth, right? But now here is a funky thing, right? So what happens is that the numerator is always 2 less than the denominator, and then you're getting this product. And this is now what's known as a telescoping product because it collapses like a telescope. In particular, as you see, the numerator n minus 2 up here also appears in the denominator 2 steps further down. The numerator n minus 3 up here also appears in the denominator 2 steps further down. Yeah? So everything cancels except the first 2 terms in the denominator and the last 2 terms in the numerator. Yeah? So I'm left with 1 over n times 1 over n minus 1 times 2 times 1, which happens to be 2 over n times n minus 1, also known as 1 over n choose 2. Yeah. But that's great because that was my success probability, right? Like now my success probability is 2 over n squared. And as we learned, 1 over success probability is equal to a factor of the running time. And this is a really silly algorithm, right? You can implement it. If you're careful, you can implement it in linear or like m Ackermann function of m time if you use union find data structure. And then you have another n square factor to get the success probability what you want. So definitely, so here is a remarkably simple polynomial time algorithm to compute the global min cut in the graph. This is known as Karger's algorithm. Okay, so for every, but here is another thing. We analyzed for a fixed minimum cut the probability that the algorithm outputs that cut. And that probability we showed was at least 1 over n squared. Now, I claim that that implies that for every graph, the number of cuts of minimum size is at most n squared. Why? Pardon?
Law of averages.
Law of averages. I'm not sure I'm able to interpret what you're saying.
Everything is greater than.
Okay, I think you're on the right path, but I don't think it's cold what you're saying. But I think you're thinking the right thing. Let's see. Yeah. Okay. I'm not quite able to turn that into a right argument. Okay. So the different optimum cuts that the algorithm could output those are disjoint events, right? Like if the algorithm outputs this cut, it definitely didn't output that cut. Yeah. So if the probability that it outputs this cut is 1/10, that cut is 1/10, that cut is 1/10, you cannot have 11 cuts because the sum of the probabilities has to sum to 1. Yes. Like so, if you have a bunch of disjoint events, then the sum of their probabilities must be strictly less than 1, or less than or equal to 1. Yeah? So because the event, the algorithm outputs this cut, or the algorithm outputs that cut, the algorithm outputs that cut, they're all disjoint, and each one of these events has probability at least 1/n². Yeah? It means that the number of events cannot be more than n², because the sum of their probabilities has to add to 1. Now, here is an interesting thing. I was promising you algorithms to cope with NP-complete problems, and we did MaxCut, which is an NP-complete problem, and we did an approximation algorithm for it. And then I gave you MinCut, which has a polynomial time algorithm, and I give you a silly randomized algorithm for it. It was also run in polynomial time. So where is the NP-completeness? Yeah. Well, if you can do something, then make it. If you can do something and it's too easy, then make it hard. Yeah. And so now what are we going to do? We're going to consider the following problem. So MinCut is a special case of the following problem called MinK-cut. I give you a graph G and an integer K, and now the task is find the partition of the vertex set into K non-empty set so that you minimize the number of edges that have endpoints in different sets. So notice Min2cut is what we just did. Yeah. Now, this is an NP-complete problem when K is considered part of the input. Yeah. So in particular, it's possible to reduce from max clique in regular graphs. So remember, independent set is this problem of finding a largest possible set with no edge between any pair of vertices in your set. Clique is the opposite thing. Find the largest possible set of vertices such that there is an edge between every pair of vertices. So that problem, of course, is also NP hard, and it's not too difficult to reduce clique to the Min-K-cut problem in a sort of one-to-one way. That's like if I can find a K-cut, then a good K-cuts correspond to K-cliques, essentially. In particular, this means that this problem is NP-complete. But we just saw a polynomial time algorithm for K equals 2. Could we get a polynomial time algorithm for K equals 3? Maybe. Turns out, for every fixed K, the probability that this algorithm outputs that K-cut is 1/n to the 2K. So now, wait, what does it mean that that algorithm outputs that K-cut? Our algorithm was contract until you have 2 vertices left. When you have those 2 vertices left, that's your cut. Okay, so what's the modification of the algorithm to make it output a K-cut? Yeah, you contract until you have K vertices left. Yeah, those K vertices correspond to a K-cut, outputs that. Yeah, and it was shown, I think, in 1995. This is a classical algorithm that for every graph in integer K, and any optimal K-cut, so a K-cut that cuts the minimum number of edges, the probability that this algorithm outputs that K-cut is at least 1/n to the 2K. Yeah, and this, of course, gives an n to the 2K time algorithm for Min-K-cut. And it was very recently, I think in like 2020 or 21, improved that it was shown, not a better algorithm, but this same algorithm, it was shown that you can shave off the 2. So it's actually just K up here. But that's a really difficult proof. So we're not going to go there. We're going to put the 2K back. And in the tutorial, I'm actually going to ask you to prove this because the proof is fairly similar to what we just did. We do have now n to the 2k time algorithm for min k cut. And notice that this is polynomial for every k. Yeah, like it's n to the 6 for 3 cut, it's n to the 8 for 4 cut, and so on. Yeah. So a very natural question is, so first one is, well, we have a polynomial time algorithm for an NP complete problem. Why didn't we show that P is equal to NP? We have an n to the 2k algorithm. Problem is NP complete. P is equal to NP. Let's collect our $1 million. Why not? Yeah, so in particular, in the NP completeness, k can be anything, including up to n, and n to the k is n to the n, which is very much not polynomial. Yes? Okay, the next question is, well, our exponent is getting worse with k, right? We have a n to the k algorithm. Could we trade that for a 2 to the k n cubed algorithm? This is what is known as FPT, or fixed parameter tractable. So notice if you try to plug in, you know, like n equals to 1,000 and k equals to 10, then there's a dramatic difference between 2 to the k times n and n to the power k. And so typically, like when you have an algorithm which is polynomial for every fixed k, you can ask, well, can you get k out of the exponent? Like, can you get FPT algorithm? Like 2 to the k times n cubed, or if you are less ambitious, what about the 2 to the 2 to the 2 to the 2 to the k algorithm times n to the 1,000? Well, it turns out that the reduction from clique is a parameter preserving reduction, whatever that means. So an FPT algorithm for this problem would imply an FPT algorithm for clique, which would collapse FPT equals to W1. We don't expect this to happen. This is a randomized algorithms course. It's not a complexity course, right? If this goes right over your head, there's nothing to worry about. Like really what I'm saying is n to the k is close to the best you can hope for, and there's good reasons to believe that. Yep. Okay. What we saw just was an algorithm that is polynomial for every fixed value of k. This is what is known as XP, which stands for slice-wise polynomial, right? For every slice of the problem, it's actually polynomial time. It's not FPT, it's a fixed parameter tractable, which is this kind of running time. Yeah, which is something we're going to see more of tomorrow. Okay, so I think this is a good place to stop the talk. I'm sharing my screen, so I can't see it.
Right. So, at some point when you started talking about NICA, does the problem have anything to do with interactive proof systems? I've seen similar calculations while proving tree colorability.
Oof. The answer is like maybe I don't know. Yeah. That's, so the question is the question asked was, does it have any connection with interactive proofs? And my answer is maybe, but I have no idea. Anything else? Yeah.
Instead of parties that you want to become, but you are waiting and I want to minimize the number of weighted different B1 minus B2 to B2 minus B1. Not taking a common part.
So you want to wait, you want to
And two sets B1 and B2, there will be some common vertex. For the age I count only from B1 minus B2 to B2 minus B1, that in that ages, in that part, not a common part.
wait, now you have one common vertex or a set of common vertices?
Set of common vertex. So
and
B1
this
and
is the set
B2
of, is the set of common vertices pre-specified?
No. I want to find a party, find not a partisan. decomposition V1 and V2 such
Okay.
that the number of edges which are not in the common part that I want to minimize. Means from V1 minus V2
Mhm, yeah.
to V2 minus V1.
And you need to have some non-triviality conditions, right? Because if you shouldn't allow to select both of them to be the same or something like this. But it's not it can't be a partition, right? Because if it's a partition, it's exactly the same as the min-cut problem.
Yes.
So you want to cover the vertex sets, you want to find
Yes, I have to cover the vertex.
you want to cover
Yes.
everything. And now you want to minimize the number of edges in the symmetric difference, right?
But yes.
But that seems to be like, how is that any different? No, okay. Yeah, okay, I'll have to think about it. I don't think I can answer it on the fly. Okay, so I think this is a good time to do lunch.